compound probability. So a compound event is a combination of two or more events. A combination of two or more events. So we're using the word and, or we're using the word or. So this is kind of like set theory a little bit, but we're going to dive a little deeper. So with and or, you have different things. You have, for or, you have mutually exclusive and overlapping. And for and, you have independent and dependent. We kind of covered independent and dependent a little bit before. But pretty much this chart right here in this page will help you out so much with this whole probability unit. Okay, so when it comes to or, if events are mutually exclusive, they are events with no common outcome. Okay, so our formula for that would be where A or B, the probability of getting A or B, all you have to do here is just add the two probabilities, which is really nice. The probability of A and the probability of B. So an example of this, and well, this is called the addition rule. So in your standards for Math 2, they say that students must know how to use the addition rule and when to apply it. So here's the addition rule. You're going to learn how to apply it as well. An example of this would be being a freshman or a sophomore. Okay, so it's not possible for you to be both a freshman and a sophomore at the same time, right? So they are mutually exclusive. You're either one or the other. Now, overlapping is a little different. Okay, these are events with a common outcome. Okay, so that will be where we have to do the probability of A or B will be where we take the probability of A and add it to the probability of B, but then we need to subtract their intersection, okay? If you think back to what we had before, say with the even and multiples of 3 from yesterday, the two numbers in the middle were 0 and 6. So if we're trying to, and anytime we did or, we never repeated them. We never counted them twice, right? So if we do the probability of A, which had the 0 and 6, and then the probability of B, which had the 0 and 6, we will be counting it twice. So then we need to subtract one of them. That's what we're talking about there. It'll be a lot more clearer once we get to it. So maybe an example of this would be being in band and being a girl. That's the example that they gave in the notes. That is possible, right? There are definitely people who are both in band and that are a girl. So you would need to subtract that intersection. If you're looking for the probability of people being in band and the probability of people being a girl, there are going to be girls who are in band that you just counted twice. So you're going to need to subtract that intersection. All right, so and would be independent and dependent. And these are events that do not affect each other. Okay, so this with and is now the multiplication rule. All right, so that would be the probability of A times the probability of B. Close parentheses there. All right, and again, this is intersection, so technically I need to do A intersection B up there. Okay, so an example of this, kind of like what I told you yesterday, is a coin and a die. So if I flip a coin, it lands on heads. That has no effect on me rolling a dice and it landed on something else, or rolling a die and it landed on something else, okay? But dependent are events that do affect each other. All right, so then with our multiplication rule here, we would do just like what we did yesterday with the, or the day before with the crayons and stuff and the marbles, replacing them and not replacing them. So independent would be without replacement. So this kind of feeds into what we did before. And I'm sorry. Independent is with replacement. My fault. Independent is when you replace it. Dependent is when you do not replace it. Kind of like the kid with the Snickers bar when he ate it, right? He's definitely not replacing it. All right, so the probability of A and B would be the probability of A, the first event, times the probability of B given A. Okay, so that means given. The probability of B given A has already occurred. So we have the coin and die for the independent, but for dependent, we would say drawing 2 cards, and then it would have to be without replacement. If you drew 2 cards and you had replacement, that would be the independent up there. Okay, so as an example, you randomly choose a card from a standard deck. Find the probability that you choose a queen or an ace. So as a little summary, we have clubs, spades, hearts, and diamonds, right? There are 13 cards in each. Okay. And then there is one of each type of card. So there's a queen of clubs, there's a queen of spades, there's a queen of hearts, there's a queen of diamonds. So there's 4 queens total, right? And then ace, there's 4 aces total. So is this mutually exclusive? Or so they gave us or, right? So what we're doing is we're looking at this first box up here, and we want to know, is this mutually exclusive or overlapping? In other words, is there such thing as a queen that can also be an ace? And that is no, right? There's not. A queen and an ace are both a type of card or an actual card name. It's not the suits, right? So no, you're not going to have overlapping here. They're just mutually exclusive. So if it's 4 out of 52 for a queen and 4 out of 52 for an ace, that's just going to be 8 out of 52. And we don't need to really worry about the percentage, but you can get it if you want to. It's 15.4%. So find the probability that you choose a king or a club. So this is different, right? So your list of cards, let me go ahead and write these out just in case you didn't remember them from before. So these 13 right here, the A being the ace, jack, queen, and king at the bottom, there's 13 types of cards, right? And then we have your suits, which are the clubs, spades, hearts, and diamonds. So anytime they say clubs, spades, hearts, or diamonds, they're talking about the suits. They're not talking about these cards here, okay? So in this case, find the probability that you choose a king or a club. So we're still doing or. We know that we're going to do the addition rule, but we have a king or a club, and a club is a suit, right? So how many kings are there? There are 4 kings out of the whole deck. How many clubs are there? There are 13 clubs out of the whole deck. However, there is a king of clubs, right? So what we would need to do is we would need to subtract the intersection, in other words, that one that goes in between them. So that would be 16 over 52. Yeah, we might as well just do the percentages. That's what they've got there, and instead of me wasting your time watching me simplify these, let's just go ahead and do the percentages. That's perfectly fine. Also, hopefully you guys know this by now, but once you get these percentages, it'll actually give you like 0.154 and stuff like that, and you need to move that to the right to get 15.4%, right? So all of these decimals will be between 0 and 1 when you first divide them out, because 1 would be 100% and 0 would be 0%. So when you keep dividing them out, make sure that you move the decimal place to the right twice. So this one would have actually been 0.308. Move it to the right twice, okay? Find the probability that you choose a card with an even number or a heart, okay? So we have 1, 2, 3, 4, 5 even numbers, but then there's 4 suits. So that will be 20 even numbers out of the whole deck. And we're still using or. So then a heart. How many hearts are there? There are 13 hearts out of 52. Now, what we need to do is these are definitely overlapping. We need to find the ones that are even hearts. Okay, so how many hearts will we have that are even? That would be 5. So we do 20 plus 13 minus 5 over 52, and that would give you 28. And that would be 53.8%. Okay? So, last one for the ors. Find the probability that you chose a heart or a spade. Okay, so a heart is a suit. A spade is a suit as well. So that will be 26. Well, for the heart, it'll be 13 over 52. We'd add it to the spade, which would be, I'm getting ahead of myself, 13 over 52. Now, is there such thing that of a heart that is a spade? No. They are completely different suits. So that would just be 26 out of 52, which would be 0.5, which would be 50%. There's your final answer there. All right, so for number 5, now we're going on to the ands, the intersections. A coin is tossed and a six-sided die is rolled. What's the probability that the coin shows heads and the die shows a 5? So what's the probability that the coin shows heads? 1/2. What's the probability that the die shows a 5? 1 out of 6. Now, we are doing and, so instead of adding, we will be multiplying. So this will be 1/12 or 8.3%. Remember, when we do and, now we're multiplying. What's the probability that the coin shows tails and the die shows an odd number? Still 1/2 for the coin, but an odd number, there's 1, 3, and 5 on that six-sided die, so that would be 3. So this will give you 1/4 or 25% when you multiply this out. Okay, so number 7, an aquarium contains 6 male and 4 female goldfish. You randomly choose one fish from the tank without replacement. Really, really big there. That means that we have a dependent event. Then you select another fish from the tank. What's the probability that both fish are male? So first off, the probability of A is the first male, right? The first one male. That was 6 out of 10. That's your chances. You don't put that fish back. Let's just say you put him in another bowl. You know, he's safe, he's fine, but he's not just sitting there flopping on the table. But he's not in that tank that we're talking about, okay? So some of you guys are like, man, that's horrible. No, he's in another bowl, I promise. So then we only have 9 fish left, and we're asking what's the probability that we pull out another male goldfish? That will be 5, because there's only 5 left. We took that other guy out. He's swimming in the other bowl. 30 over 90, that would be 33.3%. All right, so use the following information to determine if these events are independent. So in other words, the probability of A and the probability of B, if they're independent, we should be able to multiply them, probability of A times the probability of B, and that should work out, right? The probability of A intersection B. So in other words, the probability of A is 0.5, and multiply that by 0.7. Does that give us 0.35? Yes. Yes, it does, right? So I'm putting that question mark there. Does it work? Yes, they are independent. Now, if we had multiplied these out and it did not work out, then we would have known that there was some other variable, right? There was something that was dependent and it wasn't independent. There was something else happening there. So for this one, you'll see that we have 0.3 times 0.2, which should give us 0.6,